More about parallel circuits. Quite often in parallel circuits along a branch there will be more than one component. In this video I'm going to show you what happens to the voltage across a parallel branch when there's more than one component in that branch. The circuit I am going to show you has a supply voltage of 6 volts. In my last parallel circuit video I showed you how the voltage in each parallel branch is equal to the supply voltage. So every branch in this circuit has 6 volts across it. Branch 1 only contains one component, so that component gets all 6 volts. Branch 2 contains 2 components, so these 2 components share the 6 volts. How much voltage each component in branch 2 gets can be determined by looking at the resistance of each component, because the ratio of the resistance is equal to the ratio of the voltage. Let's take a closer look at that concept. We can see in branch 2 that both of the resistors have a resistance of 10 ohms. So that's a ratio of 10 ohms to 10 ohms. We can simplify that ratio to 1 to 1. Now that means that the ratio of voltages on those 2 components will also be 1 to 1. In other words, every time one resistor gets a volt, the other resistor will get a volt as well. We know that the total voltage for the branch must be equal to the supply voltage, 6 volts in this case, so we can conclude that there must be 3 volts on each resistor. We can simplify this by simply saying, if components in a parallel branch have the same size resistance, then they will get the same size voltage. What if 2 resistors are in a branch and one is twice as big as the other? Well, if one resistor is twice as big, it will get twice as much voltage. So in this example, in branch 2, the 20 ohm resistor will get 4 volts and the 10 ohm resistor will only get 2 volts. It's important to remember that the total voltage across each branch must equal the supply voltage. In this example, 2 volts plus 4 volts equals 6 volts from the supply, so that's correct. I like to use analogies to help students learn. So here's an analogy to help you understand the relationship between resistance and voltage. Think about a resistor being like a brick wall. A small wall only takes a small amount of energy to climb over. A big wall takes a big amount of energy to climb over. Well, a small resistor is like a small wall. It doesn't take much voltage to jump over it. And a big resistor is like a big wall. It takes a big voltage to jump over it. Remember, an analogy is something that we use to say one thing's like another thing. It's not actually another thing. But if the analogy helps you to remember, then great. Here's a question for you to try to make sure you understand. What is the voltage on each component? And here's the answers. The supply voltage is 12 volts, so that means that each branch gets 12 volts across it to use. Branch 1 has only one component, so that component gets all 12 volts. Branch 2 also has 12 volts across it because that's the supply voltage. It has 2 components. The 40 ohm resistor is twice as big as the 20 ohm resistor. So the 40 ohm resistor gets twice as much voltage. So the 40 ohm resistor gets 8 volts and the 20 ohm resistor gets 4 volts. 8 volts plus 4 volts equals 12 volts. So that adds up nicely to the supply voltage once again. In branch 3, all 3 components have the same resistance. So they all get the same voltage. 4 volts each in this case. 4 volts plus 4 volts plus 4 volts equals 12 volts supply. In branch 4, the 30 ohm resistor is 3 times bigger than the 10 ohm resistor. So the 30 ohm resistor gets 3 times more voltage. So the 30 ohm resistor gets 9 volts and the 10 ohm resistor gets 3 volts. 9 volts plus 3 volts equals 12 volts, which is once again the supply voltage. So that's correct. You've now covered how voltage behaves in parallel circuit branches. Well done. Hope that video was helpful. Subscribe to my channel, hit the like button, comment below if there's any videos that you want me to make, any particular topics you want me to cover. Stay safe, work hard and be nice. See you in the next one. Bye bye for now.